this is the 22nd episode for VEX or Algorithmic Design, and the topic today is about remapping. And here's the outline that I'm going to talk about today, starting from the basics of a fit function, which is going to be the basic functions for the remapping. Then do some exercises using this fit function together with some example using fit and ramp, fit and lerp functions, and some easing exercise with using fit, ramp, and lerp function. Then in the last I'm going to talk about a little bit about UV mapping, the basics of UV mapping and its exercise. And when it comes to remapping, there are many meanings for it, but in this case, what I mean by remapping is to change one value into another types of value. It could be like changing like a dimensional value to a color value or something like that. Sometimes the format of the value might change. Sometimes going from the float value into vector could be happen, or a string into a float value might happen as well. The purpose of the remapping is to change a specific analytical value into something visible or could be useful for other purposes, especially in a case where it's hard to use the value itself directly. You need a operation for the remapping so that you'll be able to use it for your visual purpose or something else. And many of the exercise what I'm going to talk about today is focusing on remapping the value so that you can use it for a visual purpose, which I think is the most easy way to understand how remapping works. And actually, I have been using this remapping concept throughout this VEX for Algorithmic Design series in many exercises. So I think if you have followed the series, many of you have already know the basics of the remapping itself. So those of you who already have some idea of what remapping is and how you can use it, this is more like a review for. Now let's do the basics of remapping by using the most frequently used function called fit function. Now first I'm going to create a geometry node. Inside I'm going to create a sphere node, and let me convert this into a polygon, and then I'm going to show the wire shaded. Now what I would like to do here is to use the slider, which is in range between 0 to 1, to change the radius of this sphere. And I'm gonna start with a really basic or really easy remapping. If the range of the target size is in between the 0 to something like 5. And I would like to control the size of the sphere from 0 to 5 using a slider which is in 0 to 1. So let's see how we can do that. I am going to create a point wrangle so that I can control every point using a single wrangle here. I'm gonna name it as simple remap. And for this first exercise, I'm not going to use the fit function, but I'm going to try to show you just with the calculation. First of all, let's try to set a maximum radius for this sphere. I'm going to name the variable maxrad and create a parameter for it named as maxrad. Okay, let's promote this one. Currently it's between 0 to 1. Let's change that later. Now I'm also going to create a parameter called scale, which I'm going to use this to change the slider in between 0 to 1. So I'm going to keep the range as it is. Now let's go to the edit parameter interface and change the max radius and between 0 to 10. So that the max radius parameter will be used to determine the maximum radius of this sphere. Currently the radius of the sphere is equal to 1. So by multiplying the value to its point position, you can change the radius. Meaning if you try to multiply the point position by some value here, like let's say max rad itself, then you'll be able to change its radius like this. Now, what I would like to show you is to use this slider scale within 0 to 1 to control the radius of this sphere in between 0 to this max radius. So let's say the max radius is equal to 5, then I want to use this scale value, which is in between 0 to 1, to change its sphere radius, the final sphere radius, in between 0 to 5. To do that, it's pretty simple. You just need to multiply this scale value to this max radius, and that's it. By doing like this, you can just, by changing this slider value in between 0 to 1, you'll be able to have a value in between 0 to 5. So this is the most basic way to do the remapping. When the minimum value is equal to 0, then all you need to do is just multiply the value in between 0 to 1 to this final target radius, the final target maximum radius. Okay, this is to show you that the remapping itself is pretty, easy. And for some cases, you don't really need like another in external functions like fit functions and so on. Just using the multiplication might work in some cases. But there are times that you want to set the minimum value as well. In this case, I have only set the maximum radius, but if you want to set the minimum radius as well, in between 0 to 1, let's say the minimum radius is equal to 2. Now in that case, I cannot use this multiplication, because if I set the scale value to 0, then the scale becomes just 0 and doesn't become 2. You have to start from 0.2 to make, or 0.4 maybe, to make it 2, radius equal to 2. So in order to do that, you can think of some more complex calculations here, complex equations using multiplications and addition and subtraction. But instead of doing that, there's just a function to do what you want to do, which is for the remapping. Remap this value in between 0 to 1 into a range between 2 to 5. And that's the function which is called as fit function. So let's try to use that. And that is the most basic and most used function for the remapping purposes. Okay, so I'm going to create another point wrangle. Let's name this remap with fit. Okay, and now what I'm going to do is to create a variable for minimum size and the maximum size. So minimum and maximum with some parameter max size. Let's promote those two, and let's also create a scale slider in between 0 to 1 as well. Okay, so let's change the range for those three. For the minimum and maximum, I'm gonna set the range from 0 to 10. And for the scale, I'm gonna leave it as in between 0 to 1. The reason I'm setting the scale in between 0 to 1 is because the range between 0 to 1 is pretty useful for many cases, especially when you are going to use it with a function like a Lerp or ramp parameter. The range between 0 to 1 is pretty convenient for many purposes. So in most of the cases, when you do the remapping, the basic range is going to be in between 0 to 1. There might be some differences in some cases, but most of the cases, when you do the remapping, the basic range could be in between 0 to 1. Okay, so for the minimum, I'm going to set to 2, and for the maximum, I'm going to set to 5 for now. Now, what I'm going to do is to use this scale slider by changing from 0 to 1. I would like to change the size of this sphere in between 2 to 5. Now, to do that, you can use a function called fit. Okay, if you look at this one, takes the value in one range and shifts into a corresponding value in new range. And the first, there is 5 parameters in order to use this fit. And the first value is the value that you want to remap. And the second value and the third value is the source minimum and the source maximum of this input value. So if you are using a scale value, which is this one, to remap, then the minimum and the maximum of this scale is in between 0 to 1. Okay, and for the fourth and fifth, that's going to be the target minimum and the target maximum. So in this case, the target minimum is this minimum size and the target maximum is this max size. So the one that I would like to change here is this scale value, which is in between 0 to 1. So this is the source minimum and this is the source maximum, and the target minimum is min size and the target maximum is max size. By doing this, you'll be able to remap this scale value into the range between 2 to 5 here. And as a result, you'll be, by multiplying the P position, the point position of this sphere, by this size, you'll be able to control the size of the sphere in between 2 to 5. And if you change the minimum size to like 1, then you can create a size in between 1 to 5 like this. So it's pretty convenient. The fit function can be used for many purposes to remap the value, the one value into another types of value. Now there are many variants for the fit functions. Currently I'm using the most general fit functions. Now first variance that I would like to show you is to skip this second and third parameter only if the range is in between 0 to 1. So there are many cases that you want to remap the value in between 0 to 1, like in this case. So for that purpose, there's just a function for it. And in order to skip those, since you already know that the value is in between 0 to 1, and for that, you can use the function called fit01. So let's try to use that. I'm going to just duplicate this node. I'm gonna name this fit01. For this one, 01. Oops, and change this function name to 01. Okay, and just remove these. So fit01 just indicates that, assume that the source minimum and source maximum is in between 0 to 1. So for that, you don't really need to specify the source minimum and maximum minimum for this function. And the result you get is the same as the fit. So if you know that the range is between the source minimum, the source range is in between 0 to 1, then you can use this one as a shorter or parameter set. Okay, which is pretty useful. Now there's also a function called fit10, so which means the source minimum is equal to 1 and the target minimum, the source maximum is equal to 0. Which is equivalent to setting, let me duplicate this one, which is equivalent to making this source value 0 and target value to the source value to 1 and target to source maximum to 0. As a result, when you use 0 as a scale value, you get the maximum value, and by increasing the value, you are decreasing the target size. So when the value is equal to 1, right, when the scale is equal to 1, then you get this minimum size. So in this case, equal to 1. And when you change the scale value to 0, then you get this maximum size. So it's in the case 5. Okay, so you can also like change the value even though the minimum is larger than the maximum value. That doesn't really matter in this case. Only the change you get is that the size relation will be reversed. Okay, which in sometimes you use this a lot as well. Okay, now to have this function, to have this effect, you can have another type of fit functions, which is called as 1, 0, fit 1, 0. So in this case, the source minimum is equal to 1 and the source maximum is equal to 0. So you can then skip those parameters and get the same result like this. So let's name this fit 1, 0. So if you know that the minimum is 1 and the maximum is 0 for the value that you're going to use for the first parameter, then using fit 1, 0 is way to go. But you can also do the same things by using fit 0, 1, then just change the minimum target and maximum target to something like this, and you still get the same result. So either way is fine. So it depends on which one looks more comfortable for you to choose to use. So either way is fine, like this. Now there's also a variance of fit function called fit 1, 1, and for that the range is a bit different. For the fit 1, 1 function, the range that you're going to use is in between -1 to +1, and the range between -1 and +1 is often used together with trigonometry, since when you use like sine function or cosine function, the range is in between -1 to 1. So it's pretty useful when you try to use fit function together with this trigonometry. Okay, so let's try to use that as well. I'm going to duplicate this one and again, and let's name this remap with fit 1, 1. Okay, that sounds good. Now instead of using a scale for this time, I'm going to just use a sine function for the scale so that I can create a value in between -1 to +1, +1. And inside the sine, I'm going to set a time value as an angle. So based on the time, based on the frame, the value will change between -1 to +1. Okay. And I'm gonna use this scale as a first parameter for the fit 1, 1 function, which is in between, which going to be the source range is going to be -1 to +1. And I'm gonna set the minimum maximums as a target. Now let's see what's going to happen. Now before doing that, I'm going to remove this scale parameter as well, since I'm not going to use this anymore. And if I play it, you can see that the sphere is scaling from 1 to 5 as like a wave. And if I change this minimum scale to 2, the scale range becomes 2 to 5. If I make the maximum size to say 0.5, it's going to be 2 to 0.5 like this, which is also equivalent to using a general fit function between -1 to 1 to min size to max size. So this will create the same effect, same remapping. If I play it, we'll just do the same thing. So using either way it's fine, but if you know that the range is between -1 to 1, then using fit 1 1 might be more easier or shorter. More effective, I guess. But in any case, I mean, using this one is also fine. You'll be able to understand what the range here. So in some cases, this might be more user-friendly to read. So, I mean, using either way is totally fine, I think. And I often use this fit function, general fit function, instead of this fit 1 1 or fit 0 1 or fit 1 0, just because it's more easy for me to understand what's going on here. Now the last variance of the fit function that I would like to show is called efit function. And to show what it does, let me duplicate this remap with fit function first and see this fit function, what this fit function does actually. And by doing it, I am going to change this scale range a bit. So I'm going to change this scale range between -1 to 2. And okay, so the range for this scale value is a bit different compared with this fit function, which the source range is in between 0 to 1. So what happens if the scale value goes less than 0 or larger than 1? Let's see what happens. If the scale values goes less, then it just stops. And if the values goes more than 1, and this one just stops again. Okay, you see? So which means is that the fit function will limit the range of the input value, which is going to be used for the first value here, the first parameter here, in between the source and the target. I mean the source minimum and the source maximum right here. Which means it's going to clamp the value in between 0 to 1. Even though I have less value or a larger value than the source range. Which most of the cases it's pretty useful. So since you don't really need to think about the if you need to set the correct range for the first input. But in some cases this might be a bit of a limitation, because in some cases you don't know what the range of the scale value is, but you want to set a specific range of this value as a minimum and maximum target. Like if you want to set a value in between 0 to 1 to be a specific angle value, like as from 0 degree to 90 degrees, and if the maximum value if the scale value goes over the 1, then you also want to increase the angle value using the same like linear scaling, which is between minimum and to maximum. So if you have typed 2 to the scale value, then you might want to change, you might want to remap it into a 180 degree by using the information that in between 0 to 1, it's between 0 to 90 degrees. So if the scale value is equal to 2, then using the same scaling information, this should be equal to 180 degrees. But if you use the fit function, it doesn't happen because the scale value is going to be clamped in between 0 to 1, so it doesn't go over this within this range. So in order not to use the clamp within the fit functions, you can use another fit related function, which is called as efit functions, like this one. Now by using this you can ignore the clamping. The clamping no more happens within the fit functions, and you can extend the output value. So let's see what happens. So if you go negative, it keeps decreasing. Like in some cases it reversed and show the inward geometry. And if you go over 1, then you get more value, and in the last you get a radius of 10. So in some cases, using this efit without the clamp function inside is pretty useful. And I'm gonna show you some exercise for this as well later. I don't use this much, but knowing that there is a function without the clamp is pretty important. Now let's do some exercise on this fit function, and specifically I'm going to show you some tips how you can retrieve the source minimum and source target. I mean the source maximum value when you don't know the range. In this case, you know that the range is between 0 to 1, but many of the cases you don't know the range itself. So for the source value. And if the value is inside the attribute, then there is a way to retrieve the minimum value and the maximum value of that attribute. So I'm going to show you how you could retrieve the source minimum and source target from the attribute and use it for the target minimum and target maximum for several purposes. Okay. So I'm gonna start with a simple exercise. I'm gonna show you, I'm gonna create a sphere and try to create a wavy surface out of this sphere. I'm gonna change this to polygon. Then let's change the frequency to 10 so that I have enough vertices. Okay. So I'm gonna use a noise function to change the height of each of the point. And by moving it to the normal direction of each of the on each of the point. Now what I'm gonna do is to try to remap this noise value, which is probably in between 0 to 1, but the minimum and the maximum is when you use the noise value, you don't actually get a value in close to like 0, close to 1. It's mostly in between like 0.3 to 0.7 and so on. So you don't know the exact value for the minimum and the maximum in that case. So what I would like to do here is to try to get the exact minimum of this noise value in the current frame, and then use that as a source minimum and target, a minimum and a maximum for the fit function. Okay, so first thing I would like to do is to calculate a noise value for each of the point based on its point position as a C value. So I'm going to use the point wrangle. And let's name this to noise value. Okay, now I am first going to create a time and the position based seed value for the noise. So I'm going to use the vector 4 as the input for the noise function. First, I'm going to create a vector 3 value by multiplying the point position by some scale value to be able to control the smoothness of the wave. So let's start with the scale equal to 1. Now, after this, I'm going to create a vector4 value named as a seed, and for x, y, and z, I'm going to use position y, position x, position y, and position z. And the fourth parameter, I'm going to set a time so that I can create some animation based on the time for the noise value. Now I'm going to create a noise value using a noise function together with this seed. Okay, so as a result, you'll be able to get the noise value which is in between 0 to 1, but you don't know the exact minimum or exact maximum in this case. So I'm going to apply this or store this into an attribute value for each of the point called as noise val. Okay. Now let's check the geometry spreadsheet by opening up the point geometry spreadsheet, and there you go. You see this noise value, and if you click here, you see that currently the minimum is equal to 0.24 and the maximum is 0.67. So you see that the range is, there's a bit of gap from 0 to and from the 0 to the minimum and 1 to the maximum. See, like around 0.25. I mean, you could still use the range between 0 to 1 to fit, but what if you want to use this minimum value for the noise value to be the minimum source, and if you would like to use this maximum value of the noise value as the maximum source value, then in that case you need to retrieve the maximum minimum out of this attribute somehow. To do that, what I always do is to use a node called attribute promote to calculate the minimum and the maximum on a specific point or primitive attribute. So attribute promote. So this is the node, and by connecting it and going into a, so currently the attribute that I would like to get the maximum and minimum is inside the point. So for the original name, I'm gonna set the attribute name, and for the original class, currently this is inside a point attribute, so I'm gonna set it as point. As a new class, I'm gonna set it to detail, since I only need one value. There's only one maximum value or one minimum value. And for the promotion method, I can set to either minimum or maximum. So let's start with the minimum, and let's also change the new name to min noise val. Okay, and I would also like to uncheck this delete the original, because if you have this one, then when you do the promotion from the attribute point attribute to the detail attribute, you do get the minimum value here inside the detail, but you will lose this original value. But you still need that for the fit function later. So you need to uncheck this delete original. Then you'll be able to preserve the original noise value as well as the minimum, the promoted minimum value. So 0.240309 is currently the minimum out of all the point attribute called noise val. Now do the same for the maximum. I'm just going to duplicate this and connect this one. And for this, I'm going to change this to maximum and name this to max noise val. Okay, and then you'll be able to have two different value, the minimum noise value and the maximum noise value. Now, since I have these, I would like to use these as the source minimum and source maximum for the fit function. Okay, now that I get the minimum and maximum, I'm going to create another point wrangle. Then let's name this remap. And use those detail value for the fit function. So first of all, let's get that minimum source and minimum maximum. I'm gonna name it as minimum value, get it from the detail, named as min noise val, and float max val is equal to detail max noise val. Okay. Now let's also set a target size for the wave as well. So I would like to change the height of each of the point position, height of this point position, so that I can change I can create something like a wavy surface. So let's create a target min height as a parameter, min height and max height. Okay, let's promote it. And let's set the range between -1 to +1. Okay, so the minimum I'm gonna set some negative value like this, and for the maximum height I'm gonna set like positive value like this. Now, what I would like to get is the finalized height value for each of the point on each of the point using the noise attribute value. So currently the noise value can be retrieved as f at noise val. Okay. And we know the range of this noise value by looking at this detail attribute called for the min value and the maximum value. So I can use fit, and the noise value is currently in between min val and the max value. And the source, the target range that I would like to change this value into is this one, the minimum height and the maximum height. So min height and max height. Okay. Now I have just created the height value, which is derived from the noise value created in previous point wrangle right here. And currently the target height is in between -0.45 and +0.45. Now I'm going to move the point position to a normal direction, multiply by this height, and let's see what happens. And also let me connect the normal node so that the shading becomes correct. Now if I play it, you can see that the height of each of the point is changing based on the noise value, which is using the time as the seed. And if I change this minimum height and maximum height, you can control how much it moves. If you make it really small and very high, you can create like this. So you can make sure that the minimum height is always in between. The minimum is always -5, and the positive is always like 0.5 or 0.6. Which is pretty useful. And you can go back to this point wrangle, and let's say you can change the scale to change the smoothness of the movement. If you make it higher, you can make it more like a wavy function. Make it smaller, you can make it more smoother, like this. Now that I have set at the height based on the fit function, let's also set let's create another value using the same fit function and using the same source range. Let's say I would like to set the color based on the noise value as well. So for the colors, you need to have the different target value. So let's see how we could do that. First, I'm going to create a float value based on the color for the color value, which is the target ranges in between, let's say in between 0 to 1. Now I'm going to create a remapped value, which is in between min val to max val for the noise value, and for the target I'm going to set from 0 to 1. Okay, now I am going to create an attribute called col and store the value that I've just created. Okay, spell mistake, min val. Now in the last, I'm going to create the color node and set the ramp from attribute and change the attribute to col. And since the range is between 0 to 1, you can directly use this with the attribute that I've just created. And you can set the color range as you want. So I'm gonna set from red to yellow. We'll create something like this. So based on the noise value, I'm changing both the height of the point, height of the surface, and also the color, which is in both of the value in different range, but you can just do it using a multiple fit functions like I did here. So this is just a simple exercise for the fit function. Let's try to do another exercise. In this case, I'm going to try to use a efit function. So what I'm gonna do, I'm first going to create a bit more complex geometry. So I'm going to, let's say, use a squab. This one. Okay. Now, what I would like to do here is try to calculate the distance from specific point on top of the surface. Could be somewhere around here, it could be somewhere around here, and so on. And try to calculate the distance through the surface. So from here, from this point, we would like to create a distance to each of the point on a surface. So from here to here, maybe the distance is 1, this here is equal to 2 and 3 and so on. So from this point position, I'm going to use the function called surface distance to calculate this distance on this surface and use that value to change the waviness or the wavy height for this surface. So what I'm going to do is to change or remap the distance which is on the surface to an angle for the trigonometry like sine function or sine function, and use that cosine or sine function value to change the height of the surface. So in the result, you should be able to get a wavy surface using the center point as the center of the wave. Okay, so first thing first, let's try to choose the center point of the wave or ripple. I am going to create a add node so that I can create a single point. Let's set the point position using this show handle here. And let's move this to somewhere close to the head. Could be anywhere, but I'm gonna set it somewhere around here. Alright, now first thing I would like to do is to determine which point on this surface is the closest to this guide point that I've created using add node. Now I am going to create a point wrangle so that I can control all the points at the same time for the squav and connect this add node to the second input. Let's name this remap surf or ripple surface. Okay, so first thing first, I would like to get the point number for on top of this point number for the squav to determine which point number is the closest to this added point, which is currently right here. And you can do that, we can retrieve that using a new point function. So let's do that first. I am first going to retrieve the point position from this add node, named as nPos point from the second input P. And there's only one point, so I'm gonna set to 0. Now that I have retrieved the point position for this add node, I'm going to retrieve the point number on top of the squav, which point number is related or closest to this add node, using a near point 0, using nPos as a guide position, search position. Now, as a result, you'll be able to get an npt variable, which is the number of the point on a squav. So let's check this out first. Okay, I'm going to store this npt as an integer attribute to each of the point. Each of the points should have the same value here. Currently it says 414. So let me change the size of the font to a bigger scale, like large. Let me save this as a result. And let's show this point number. And let's see where this 414 point is at. And if you look at carefully, so here it is. Here's the point which says 414 and should be the closest to this added point. Okay, looks correct. So that's good. Now, going back, I'm gonna delete this. Now the next thing I would like to do is from this 414 point, I would like to calculate the distance between this point to all the other points on the squab surface. Okay, and I don't want to calculate like a linear distance like from 414 to 583. I don't want to connect with the line to calculate the distance, but instead I would like to calculate the distance on top by creating a trail on top of the surface. Okay, and use that distance for the remapping for a later purpose. Now to do that, you cannot just use the distance function, but instead what I'm going to use is the function called surface dist. Now if you look at the parameter set for the surface distance, it's a bit complex compared to a normal general distance function. It says finds the distance of a point to a group of points along the surface of geometry. I think it can get a shortest distance to a closest point on the point group. Now for each of the point, for inside the point wrangle, I'm going to search for the distance between the initial point position to each of the point. So I don't really need the point group in this case. So for the point group, it can be a single point number, could be this number for 414, I think. And for the p attribute, you can determine like what attribute could be used for the distance value measurement. And since I would like to use the Euclidean distance, so I'm going to use p, the point position, like this one. And for the search point, I can use, for each point number, I can use like pt_num. And as a output, you'll be able to get the closest point, which I don't really need as an information, but you still need it as an output value. And the distance metric, I can choose either based on the edge or a surface. The edge is used to calculate the distance by following the edge. So that might not give you a smooth result. So I'm going to use instead the surface, okay? Which should give you a bit more smoother value. So let's try to use this. We're just going to copy all these and then paste it right here to use it. So float distance is equal to this value here. Okay, it's pretty long. So for the first one, it's 0. And for this PT group, I can say like I2A and PT. Okay. So converting this point number that I have found into a string, since we have to set a group value. Group value have to be in string, but since we are only searching for a single point, I'm just going to convert this into a string, and that's fine. Now for the p attribute, we're going to use the point position value. And for the search point number, I'm going to use pt_num. And then for the closest point, I have to make some output parameter. So we're going to name it as closest. And give it here, though I don't use this. And then for the final parameter set, I'm going to set it as surface instead of the edge. Okay, now as a result, you should be able to get the value. Okay, spell mistake. It should be I2A. So you should be able to get the distance from the original point to each of the point. So let's check this out as well. I'm going to store the distance variable or attribute. And let's create the marker to check out each of the distance on each of the point. So I'm going to create a marker called distance. And if I look at this, now the 0.414 should give you a 0, so that looks correct. And if you go farther and further, you should be able to have more higher value, and it looks correct, I think. Right. Now let's check this out first, to use this value as a color value to see the color map on this surface, how it looks like. So I'm going to let me first test if I can change the color of this surface. Since there's a texture on it, I might need to remove that texture. Okay, so the color, if I try to change the color, it doesn't work because I have the texture here. So let's try to delete the texture first. I'm going to delete the attribute using attribute delete, and delete the primitive where it stores all the material related value. Okay, did it delete it? Nope, it's not deleted. So for the primitive attribute, I would like to delete all. Okay, now it seems to work. Okay, now going back to the ripple surface, Let's remove this one. And just like I did previously, I'm going to try to retrieve the minimum and maximum of this distance value first. Okay, so it currently it's between 0 to 3.25 and so on. So let's retrieve the minimum maximum. In this case, the minimum is always equal to 0 since we're calculating the distance. So we only need to retrieve the maximum. So let's create a single attribute promote and get the distance and change the original point to point and new class to detail and set the maximum. Change this to max dist and uncheck delete the original, and by using this you'll be able to get the maximum in the detail as a max distance. Now let's create a point wrangle again, or maybe without using a wrangle I can directly connect this point color node and ramp from attribute and set it to distance. Only thing I need to do is to set the maximum here. So you can use the expression for a detail and use the current input using op input. This is to retrieve the current node value, okay? And the name of the detail attribute is called max dist and at 0. So as a result, you'll be able to get the maximum value, which is stored inside the detail attribute with an expression. Now I can change this color, let's say starting from red, and becomes yellow, becomes green, becomes blue, and finally becomes magenta. So you can see the color map, it shows the distance from the single point to each of the point on the surface. So you see this kind of a gradient value. Okay, now what I'm going to do now is to use this distance value for as an angle value for the trigonometry. And for that, I am going to use a efit function which doesn't clamp the source value so that you can extend the range to the unlimited. So let's go back to this ripple surface, and then first thing first, I'm going to create an angle from the distance using a fit function, but in this case efit, so that I don't have to clamp the source. Now the source value is distance, obviously, and let's say we don't currently know the range, the maximum or the minimum. We do know the minimum, but we don't know the maximum, okay? So I'm going to set the minimum source to 0. And for the maximum, I'm going to create a parameter like a range or a max dist, okay? And then I'm going to set as 0 to pi. Maybe I'm going to name this to range distance, okay? And for the target, I'm going to set as 0 to pi multiplied by 2. Which means it's between 0 to 360 degrees in degrees. Okay. Now let's promote the range distance. Now this means is that if I change this range distance, the distance which is between 0 to let's say 0.5 is going to be used as the range between 0 to 2 pi. And if this range distance goes above 0.5, like let's say 1, I am going to keep the range distance as it is. But if the distance itself, if the distance that I have retrieved from this surface distance goes above this range distance slider value, let's say the distance is equal to 1, then that means it's double size of this range distance, right? So if the distance is equal to 1, it's 2 times bigger than this range distance. So that makes it's this target size is also 2 times bigger. So you'll get 4 times pi value in this case, if the distance is equal to 1, since efit doesn't clamp the value. And if the distance is equal to 2, then you get 4 times bigger value than the range distance, meaning you get 4 times bigger angle value. And angle value is being repeated, being looped through 0 to 360 degrees, meaning 0 to 2 pi. So more angle value you have more repeated wave numbers, So as a result, by using this angle as a value for the sine or cosine, you'll be able to have different numbers of a wave by changing this range distance. Now, what I'm going to do is to try to use this value that I have calculated for a surface distance, how much it goes off the surface, how much the point should be moved to the normal direction on the surface. So I'm going to control the point position by using the normal direction on the point multiplied by the value, or maybe I can remap this value as well. Since the value is between -1 to 1, I can use the function like fit11. So let's create a range value. Height is equal to a fit11 for the value, and the target, I could change the target to, let's create the parameter like target min and target max. Okay, and multiply this height with the normal. Okay, now if I change this T max to target max, you can see the surface has been popped like a wave, and also changing this T minimum, the target minimum, also to the negative. You can see that it can control how much it extruded or moved to the normal direction, and using the distance from the point as the angle for the wave. And if I choose this, change this range distance, make it smaller, you'll be able to have more waves. Make it bigger, you have less wave, but smoother wave. You see? Yes. Okay. And let's also try to change the color value as well here. So currently I am using this distance as the color value, but what I'd like to do is to change this value that I have retrieved out of the sine to a value in between 0 to 1. So float call, and use another fit11 function to change the range between 0 to 1. Okay, now I'm going to multiply this call to a distance. And let's go back to the color, and now you have more interesting color range like this. And you can, so at some point you have at the minimum target position you always get 0 for the color. So that's because you're getting a red color as a like this. Now for this one, let's make it like a black or white, maybe black, or keeping it red is fine, I guess, which is interesting. And you see like this. Now if you go back to the ripple, and if you change this range distance, you can clearly see that you have more waves if you have range distance smaller. That is because only in between, if the distance in between 0 to 136, it's being treated as 0 to 100, 0 to 360 degrees. So the shorter distance gives you one wave. If you make this distance bigger, then the bigger distance gives you one single wave. So, which is in between red line to another red line. Make it bigger, you have less wave, and so on. So this is one of the practical way you could use efit, which could be useful when you don't have a clamp function. Okay, especially it works well with the angle together with the trigonometry like this. Now let's finish this up by adding some time-based value like for the angle, so that you have animated ripple wave, which is interesting. The next thing I'd like to show you is to use a fit function together with a ramp parameter, which is also a practical stuff you use a lot in a procedural modeling together with the VEX. So let me show you how you can do that. I am going to start with the grid node, and let's change the rows and columns numbers to something like 51 and 51, so that make sure that you have the point on the center for this grid. Okay, now I am going to calculate the distance from the center point to each of the point, in this case linearly. Okay, so I'm going to create a point wrangle. Let's name this Dist. Let's calculate the distance using the distance function between the 0, 0, 0, which is the center of the space, which is also the center of this grid, to each of the point on the grid. And let's store that as an attribute. Now, like I did last time, I would like to retrieve the minimum and maximum of this distance. Now the minimum is clear, which is 0, since there's a point on the center for this grid, so the minimum always 0. So I only want to retrieve the maximum of this distance. So let's create an attribute promote. Let's set this to set the new class to detail, and for the original name it's distance. Let's set that to maximum, and the name for the detail attribute also is max dist, and do not delete original. Okay, now let's check this out. You still have the distance, and the maximum is 7.07. Okay, that's good. Now let's create another point wrangle, connect, and let's name this ramp remap. Now let's retrieve the detail value first, the maximum value. So float max distance is equal to detail 0 max dist. Okay, and we know that the minimum distance is 0, so we'll skip that. So and I'm going to create a height value based on the distance and try to change the height of this point on the grid to be moved in upward, in this case a y direction. Okay, so height, and using the fit function to remap the height value from the source, which is right here, to a specified target value. So fit a distance, which is currently in between 0 to max distance, to some specified value, but in this case I'm going to specify the value in between 0 to 1. Okay, and let's change the height like this. Okay, maybe I might want to change the height so that the center point will be higher and the edge point will be lower. So I'm going to make it 1, 0 like this. Now if you want to have more height, you can increase this like this. Now this is currently this is a linear height changement. Now what I would like to do next is to remap this value that I have created here using the fit function using a ramp parameter. So by using a ramp parameter, you can define your custom curve to change how much it should be going upward and how much it should go upward in specific distance value. So based on the distance value in between 0 to maximum distance, I might want to change how much it should go up based on its distance value. And to do that, you can use this ramp parameter. And to use the ramp parameter, it is a good idea to first change this range that you have got between 0 to maximum distance into 0 to 1. Okay, so let's do that first. I'm going to first remap this distance value between 0 to 1, and as a result you'll be able to use it directly for a ramp parameter. So let's update the ramp parameter using update this height parameter or height value using a ramp parameter using chramp. Let's name the ramp parameter as ramp and height. Okay, and promote. And this is the curve that's used as a default value. So currently it's just a linear curve. But by changing this curve, you'll be able to control the output from the input. The input ends in the x axis and the output is on the y-axis. So currently if you input 0.2 as an input, you get 0.2 as an output, so which is 1 to 1 remapping. So as a default, by using this linear ramp doesn't give you any changes, but once you try to change this curve here, you see there's some changes happens on what you get as a result. Okay, so instead of using a linear curve, I'm going to make it as a B-spline. Also this one to B-spline, so that you'll be able to have a curvy graph like this. Okay, now now that I have remapped this value, which is between 0 to 1, I can remap this again to a final source value. And currently the remapped value, the remapped height value is in between 0 to 1. I can use a fit 01 function to change this to a target value. And I want the center one to be higher, so I'm going to set the max height for the target minimum and 0 for the target maximum. Or you could maybe you could use 10, fit 10 and make 0 max height as well. Oops. Either way is fine. Okay, now let's promote this max height parameter, and let's also change its range from 0 to 10. And if I change this value here, you see that you don't know you now see more curved changement on the height compared with the linear distance changement you had previously. So previously it looks like this, but by adding a ramp curve, you'll be able to control how much it changes its derivative. You can change the derivative of the height like this. So this is another practical usage of fit together with a ramp function, a ramp parameter, which you do use a lot for many purposes. And this is one of the basic example how you can use a ramp parameter together with the fit. Okay. Now the next basic example that I would like to show is to use a fit function together with a Lerp function. The Lerp, if you look at the documentation page for the Lerp function, it says performs linear interpolation between the values. So you can change one value into another value smoothly, linearly using this Lerp function. And you have 3 parameters in order to use this lump parameter. One is the source value and one is the target value, and amount is the value which should be in between 0 to 1 to change the output value from value 1 to value 2. So if the amount is equal to 0, you get value 1. If the amount is equal to 1, you get value 2. If you use 0.5, then you get the middle value between value 1 and value 2. So since the amount is in between 0 to 1, it's really useful to use together with the fit function. So use the fit function first to convert some value range to a 0 to 1. Then you can use this Lerp function to control the value from one value to another value smoothly. So let's see this combination. First of all, I'm going to create 2 spheres as a polygon. So let's make a polygon. Let's set the frequency to 4 for both. Okay. So this one and this one. Now, for the second sphere, I'm going to... Now for the first and second sphere, I'm going to create a different transform and set a different size for each of the sphere. So let's make this scale randomly controlled for each of it. Like this. So first one looks like these, second one looks like this. So what I would like to do is to create a smooth lerp between the point position for this sphere into this point position for this second sphere. So change the shape between this one to this one using a lerp function. Okay, so let's create a point wrangle. So let's connect the first one to the first input and second sphere to the second input. And let's name this lerp shape. And first of all, let's test out this lerp using a parameter, a simple parameter. So I'm going to create a val with the parameter called val, which is in between 0 to 1. Okay, and together with the lerp. So what I would like to do is to change the position of this point position for the first sphere into a second set of the sphere, the point position for the second sphere. So what I would like to do is retrieve the point position for the first circle and this point position on the second circle, the sphere. So the current point position can be retrieved by at P, but second point position can be retrieved by using a point function from the second input, and the attribute that I would like to retrieve is P at ptnum. Since we are dealing with the same sphere with the same point numbers, I can just use ptnum as it is. Now that I have got the second point position, second sphere's point position, I can now use the lerp to get the interpolated position. So lerp and at p and pos. So this is the source position, this is the target position, and we can use this val, which is in between 0 to 1, to control the to get the interpolated position. Now let's update the current point position to this interpolated lerp position. Now currently it's 0, so you get this source points, but if you move this to 1, you get this final sphere geometry, which is this one. Okay, easy that is. Now what I would like to do now is to replace this value, which is currently 0 to 1 slider, but some different range value, something like a sine based value using a time for the parameter. Okay, so in this case, this will give you a value in between -1 to 1. Now if you use a -1 to 1 for the interpolated value, the interpolation, the lerp value doesn't clamp the value. So we'll try to use the -1 for the lerp and give you some weird result like this. So you have to remap this value into a 0 to 1 somehow. And that's where you want to use the fit function. So val is fit value, which is in between -1 to 1 to 0 to 1. And now you'll be able to have a value in between 0 to 1, which loops like this. Or instead, you can use fit 1, 1 and just remove those two source values, which gives you the same result for the sine function. Okay, so this is a basic example for using lerp together with the fit function. Now let's do a bit more complex exercise. Let's say we have a bunch of spheres in the space and we want to create an interpolation between those multiple spheres. Try to move a sphere from one sphere to another sphere, then to the next sphere, and then to the next sphere, and continue creating this interpolated movement within from first frame to the end frame. And if you go back to the end frame, if you go to the end frame, then go back to the first frame to loop through again, going through the same path. So if you have 5 spheres, then first sphere to the second sphere to the third sphere to the fourth sphere to the fifth sphere, and fifth sphere to the first sphere, and then do the same thing like a loop. So let's try to do this looped animated interpolation using a fit function and lerp, together with some frame-based value as well. Okay, so first of all, I am going to create a bunch of sphere in the space. I'm gonna start with the really big sphere. Let's say the radius is equal to 4. Okay, and I can convert this into a polygon. Let's set this frequency to something like 5, and then I'm going to create an ISO offset to convert this sphere into a volume. And let's change the uniform sampling diffs to 50. And I'm going to use a scatter node to have a bunch of points inside this volume. Now this, the number of this point will be related to the number of sphere that you want to interpolate with. So I'm going to set this to 5 for now, so that you have 5 spheres in a space. Now, I also would like to change the scale value for each of the sphere. Also would like to apply some ID value as well. So let's do that by using a point wrangle. And let's name this scale and ID. Now the ID is, I'm going to just use the ptnum, which is the point number. So the ID starts from 0, and if you have 5 points, the maximum ID value will be equal to 4. I'm also going to create a random scale value, vector scale, using a random. Now the random value for the vector will create a XYZ coordinate random value, and all those coordinate is in between 0 to 1. And now I don't want to have a 0 value for the scale, so I would like to make the minimum a bit more larger than 0. So would like to refit this random function or random vector into something different. Okay, so let's create a minimum and maximum value for the target. And let's use this to remap this vector itself for all x, y, and z coordinate. Now, the final scale, I'm going to create it as an attribute. So v@scale is equal to, I'm going to use fit 0, 1. That's because I know that the random value scale, all the x, y, z coordinates in between 0 to 1, so I can just use fit 0, 1 for the scale. Okay, actually this fit function can be also used for the vectors, which is also great. Not only for the float, but could be also used for the vectors. Now for the target values, I could use a float value, but still I can get a output as a vector, so that's a good part of it. So for the target minimum, I'm gonna use float, this min value, so min. For the maximum, just use max. Okay, now let's set the minimum value and the maximum value to something. And let's check out the point attribute to check if this scale is being randomly created and it's in between the minimum and maximum range. And I think it is. Yeah. Right, that looks good. Now, what I'm gonna do next is to create a sphere node again. And this time I'm going to set this point, I'm going to set this as a polygon again. I'm going to keep the uniform scale as 1 since the radius is going to be used as a radius. For the frequency, I'm going to increase a little bit more, like 4. Okay. Now I am going to use copy 2 points to move those sphere into each of the point with a different scale, so that you'll be able to have this kind of a flattened sphere or ellipses like this. And what I would like to do now is to move one sphere to another sphere, to the next numbered sphere, by changing its shape using a lerp 1 by 1 during this time frame. That's what I would like to do. Now let me increase a little bit of size. In terms of the scale, let's change the maximum range like 5 as maximum. Okay, something like this. Doesn't matter if it's over, it has an intersection since we only see one sphere at a time. Okay, that looks good. Let's say 2.5. Now let's do some interpolation movement using the time-based value. Okay, so I'm gonna create a point wrangle first. I'm gonna use this basic sphere as a basic start geometry. And then I'm going to connect this copy 2 points result as a guide geometry. And if you look at the point attribute, there is a value called ID, and which indicates which points belongs to which sphere. Okay, so the ID can also be considered as an ID for the sphere. Currently we have 5 spheres, so we have 5 IDs from 0 to 4. Okay, and for the third input, I'm going to connect this point, which is going to be used to determine how many points are there. So currently we have 5 points, so by connecting to the third input, I'm going to retrieve this number 5 to determine how many interpolations we need for a single timeline. Okay, now let's change the name to a lerp move. Okay, the first thing first, I would like to create a integer value which is going to be used for the ID, and this ID is going to be used to determine in which sphere right here, which of the sphere is going to be shown as the base for each of the frame value. And since we have 5 spheres, we want to divide the frame by 5 first. So, and if you have 240 or let's say 250, if we have 250 frames, then if you divide by 5, you have 50 frames for each. So for each 50 frames, you want to have one of the sphere being shown as a base. Okay, and for, let's say, the first sphere is this one and the second sphere is this one. Then within the first 50 frame, I would like to start with the basic shape of this sphere, and then from 1 to 50 slowly I want to move this to a second set of sphere, creating an interpolation position. And from 50 to 100, let's say the next sphere is this one, then I would like to change this shape to this shape, interpolating using a lerp, and continue doing that until the last. From the last 200 to the 250, I would like to convert from that last geometry to the first geometry. Okay, so that's what I would like to do. Now, so to do that, I first need to retrieve the number of spheres, and you can retrieve that by counting the number of points from the third input. So let's do that first. Int a count is equal to n points 2. So I'm just have counted the number of points from the third input. Now, I would also like to convert the frame value, which is currently from 1 to 250, into a float value, converted into a value in between 0 to 1. Okay. Now, to do that, I can use the fit function again. So fit currently the current frame value is in between 1 to end of the frame. In this case, I'm gonna add one more to this one for later purposes. I'm gonna explain why next, and change this to 0 to 1, so that the last value, and when the frame goes to 250, the f value won't be equal to 1, but something close to really 0.999 or something. Let's check this out. I'm going to create a attribute called f, and let's see what it looks like. So the maximum value is 0.996, and that's fine. And there's a reason why I don't want to have 1 as a last frame value, and that is because if I try to convert this frame value into an integer value, like from 0 to 50, from 1 frame to 50 frames, I want to use the ID equal to 0, and the next one is 1 and 2 and 3 and 4. If you have a 1 value and 1 for the final value, then you're going to have a 1 extra index, which is an unnecessary index value if you use like a function like floor function, and you'll see this during the equations that I'm going to create now. Okay, now the next thing I would like to do here is to convert this f value, which is in between 0 to 1, to a integer value. And to do that, what I'm going to do is to first of all calculate the remains using the 1 divided by the count. So first I'm going to divide the whole and divide the value 1 by count. So in this case the count is 5, so as a result you'll be able to get 0.2 as a result in this case. Now using this 0.2 value, I'm going to calculate the remain together with this frame. Okay, and the frame currently is in between 0 to 1, remapped into 0 to 1. Okay, so if you try to calculate the remains with the 0.2, then you'll be able to split the range of this frame value into 5 sections, and for each 5 section you'll be able to get from the value in between 0 to 2. So from first frame to the 50 frame you get 0 to 0.2, and from 50 frame to 100 frame you get 0 to 0.2 again, and from 50 frame to 150 frame you get another 0 to 0.2 frame again, 0.2 value again, and so on. Okay, so which is really useful, which is going to be really useful later on. So let's do that. So what I'm going to do is to calculate the remains using modulus with this value 0.2, like this. Now that we have retrieved the value in between 0 to 0.2, I am going to remap this again into 0 to 1. Currently the range of this value is in between 0 to 0.2, but for more convenience I'm going to remap this again into a value in between 0 to 1, so that for frame 1 to 50 you'll be able to get a value in between 0 to 1, and 50 to 100 you get 0 to 1, and so on. To do that, I mean, you don't really need to use the fit function, but you can just do that by multiplying count back again, which is equal to 5. So 0.2 multiplied by 5 is 1, so the maximum value will be 1 and the minimum value will be 0, like this. And let me also change the value name, the variable name, like I'm gonna name it as FF, okay? Now I also want to retrieve the integer value, like which sphere is going to be used as the base for the Lerp, okay? So to do that, I am going to create another value called I as an index, and by multiplying the frame value, which is for this one ends between 0 to 1, by a count, which is equal to 5. You'll be able to have a value in between 0 to 5 index, 0 to 5 float numbers. But to use it for index, I need to convert it into a integer, so I'm going to use floor. So as a result, you'll be able to have a integer value in between 0 to 5. Now this is the case I don't want to have a integer value equal to 5, because there's only like 5 sphere, and index 5 means that you need to have a 6 sphere. So that's kind of a reason why I have limited the maximum value of the f to 0.99 something, so that if you use the floor function, the integer value will be always less than 5, meaning 4 in this case. So as a result, you'll be able to get integer value in between 0 to 4 in this case. So in total, you have 5 different numbers for each of the frame values. And that's what we want actually. Okay, now that we have enough information, what I'm gonna do is to first retrieve the point position of the sphere, which is at which when the sphere's ID is equal to I, okay, from the second input. Okay, so using I'm going to search for the sphere which shares the same I value, the ID value, or the ID attribute. So this is where it says ID. So when the I is equal to 0, I'm only searching for the value which have the ID equals to 0, which from here until right here. And if the I is equal to 1, then I'm only going to search for the sphere which have the ID equal to 1. And to do that, you'll be able to use the function called find attrib val. So int, and you'll be able to find a bunch of point numbers because each sphere has several numbers of points which construct a sphere. So what you get as a result is the array of point numbers. So npts1 array is equal to find attrib val. From the second input, I'm going to search for the point class and ID and use I as a search query. Now as a result, you'll be able to get a number of points which construct a sphere, and out of this point array, I only want to retrieve one point number. And since we are using a point attribute together with the base sphere, which shares the same point numbers as the the spheres that I have created here, because right here I have just copied this sphere as a guide, as a template, using the copy 2 points. So all the copied spheres on a space shares the same point structures or same point numbers. So what I could do here, after I have retrieved the point array, I can retrieve the related point number by accessing this array at ptnum. Okay, and then you could retrieve the position at npt1, and this position is going to be the position on some of the spheres point position based on the frame value. If I is equal to 0, then you get the first sphere's point position. If I is equal to 1, then you get the second sphere's point position. And let's check this out by overriding the current point position to the npos1. Okay, now starting from the first frame, currently, okay, let's see. Okay, I think something must be wrong. Let me check. Okay, one mistake. This has to be 1. Since we are retrieving the point position from the second input, this has to be 1. Now, currently, so when the frame is at 1, it's using this sphere as the starting value. And if I change this, goes over 50 frame, switch to the next sphere from this copy to sphere, and if you goes on and on, it switches its position like this. So it looks okay. It goes over all 5 spheres by every 50 frame. Alright. Now next thing I'd like to do is to actually move this sphere from one position to another, not just by jumping, but using a Lerp. Smooth transitions using Lerp. Okay, interpolation. Now to do that, you need to have a next point or next ID's sphere position. Currently we have a point position of the sphere at I index, but you also, in order to create a Lerp or interpolation, you also need the next sphere's point position information as well. So to do that, you can just do it by searching for the I+1 ID. Okay, so int npts2 find attrib val from the second input, point class ID with I+1. Now, one thing you need to be careful if you want to create a looping animation, if you want to go from the last sphere to the first sphere, then you need to make this goes back to 0. If in this case we have 5 spheres, so when the I is equal to 4, that's the last index. And if you say 4 plus 1, you get index equal to 5, which doesn't really exist in this case. So in that case, you need to, if the I is equal to 4, then the next number should be equal to 0. Okay, so to do that, what you can do is to calculate this by using the modulus, or calculate the remains with the count. So when the I plus 1 becomes 5 and divided by 5, then the remains become 0. So that's the result of what you want. So by calculating with the modulus, you'll be able to reset this into 0 when the I becomes more than count. Okay. And then let's retrieve the point number like just we did using a ptnum, and then get the position from the second input at npt2. Now that we have two positions, and if I try to change this n plus 1 to n plus 2, you get the next sphere's positions. Now, what you just need to do now is to use a Lerp function to smoothly connect between the first to the second, based on the value between 0 to 1. So you do have a value called ff. You have created a value called ff, which is in between 0 to 1 for every 50 frames. So you can use this for a Lerp amount. So what you can do, Lerp n pos 1 n pos 2 and ff, and as a result you'll be able to linearly move the sphere from one sphere to another sphere like this. Okay, easy as it is. Now let's try to extend this movement a little bit using a ramp function to make the movement a bit more interesting. Okay, so I'm gonna duplicate this one, and let's name this Lerp move with ramp. And for the ramp parameter, you can just add one line after we have created the ff value. I'm going to update this ff value, which is in between 0 to 1, so you can just directly use it with the ramp. Okay, let's name this ramp and ff. Promote the ramp parameter, and let's change the curve to something like B-spline and create this kind of curve. If you try to see the result, you'll be able to see a bit more interesting movement going from one place to one place. For first few frames, the movement becomes really fast and then slowly goes to the target destination. And by changing this one, you can control how it moves. This one slowly starts to move and comes to the target really fast. Or could do like this, more like a ease in, ease out. Okay, so seems to work pretty fine. And if this could even work even if you change the number of points, like if you change it to 20, this still works. Change this to 10. Okay. Now let's also try out a little bit of a little different function as well, which we haven't used yet, which is called as a smooth function, which is a simple functions to create a ease in, ease out, a interpolation. Instead of using a ramp by using your own curve, you can easily create this ease in, ease out effect using this sample or smooth function. So let's name this smooth. So instead of using ramp, I'm going to use the function called smooth. Okay, and if you go to check for the smooth function here, so you have a value 1 and value 2 in amount. So this is pretty similar to a Lerp as well, but it only can create a float value. So I am going to change the FF value to use it with this smooth. Okay, so it's for the smooth, I'm going to move this FF value from 0 to 1 using an FF. And as a result, you have this easing, ease out movement without using a ramp curve, which is convenient at some situations. Okay, now let's remove the ramp because we're not using it. Now let me also show you a basics of UV remapping as well. There are a bunch of things you can do with the UV, so maybe this could be another topic for another video, but just for this sessions, I'm gonna show you some basic way you can use UVs for the remapping. Okay, so let's start with some complex geometry like big head. Okay, and let's assume this doesn't have a UV yet. Well, it does have currently, but I'm going to ignore the current UV value. I'm going to recreate the UV value using a node. So I'm going to first create a attribute, delete attribute to delete the material information by setting asterisk to the primitive. Okay, now I am going to recreate the UV using UV flatten. Okay, now I am going to check this preserve seams on, turned on, or might be okay without. Maybe using preserve seams might be better. Okay, and then it already looks good, I think. And I also would like to check in this seams output groups as for the seams. Okay, and that because I would like to split the surface where the seams are being happening, where the seams edge are there. So I want to trim this out or split those surfaces where you have the seam. Okay, and what I would like to do is to flatten all these planes into a surface as a geometry using a wrangle or VEX. Okay, now that I have a new UV value, let's go to a vertex value, and you see this UV information here, which is in between 0 to 1. Okay, so what I would like to do is to use this UV value to use it for a position of each of the point. Now currently the UV value is used to determine for the texture positions, but I would like to use this UV as a direct point position of the surface, and maybe being able to change between the point position to the UV position using a Lerp might be interesting. So let's try that out, which is pretty easy. So right after I have created the UV flatten, I am also going to create a quick shade so that I can see which UV corresponds to which position. Okay, so it looks like this right now. Now what I would like to do is to flatten this surface based on the UV positions, and to do that it's pretty simple using point wrangle, and let's name this flatten. And first of all, I would like to retrieve the UV value for each of the point. So first thing you need to do is to get the corresponding vertex number for each of the point. You can do that by using a function called point vertex, which will give you a linear vertex number. So 0 pt num. Okay, and using the vertex number, you'll be able to get the vertex attribute, and the vertex attribute that I want to retrieve is this UV. So let's retrieve that. So vector UV is equal to vertex 0 UV at VTX. Now, what I'd like to do is to change the point position itself to a UV. And by doing it, you get something like this. Now, the problem with this one is because all the edges are being connected, so you do see those ugly faces connecting to one of the edge to another edge. So one thing you need to do before is to split those edges where the seams are happening. So we can do that right after the UV flatten using a edge cusp, and now you'll be able to split it. And probably currently it just automatically splitted the edges by the seams, but you can also define which seams should be splitted by determining the group as well. So in this case I'll put seams, but seems like you don't really need to set any groups for this one. Or not. Oh yes, okay. If you don't have this output seams, does it still work? Yeah, it still seems to work. So I guess we didn't need this one after all. Okay, so that's how it looks like when you flatten the point or geometry to the UV space. Just like the UV mapping face you always see when you do the texturing or texture painting. Now, to make it a bit more interesting, you can use like a Lerp to go from a point position to the UV smoothly using something like a val function or parameter from 0 to 1. So first it looks like 3D geometry, but then by raising this up, it becomes a flattened UV plane, which is, as a practice, is pretty interesting and show many potential what you can do with it. Okay, so that's just the basic of using UV. Now let me show a little bit more complex example using UV to how you can use this UV value for a remapping purposes to change the surface expression using a UV. Now specifically what I'd like to do is to use the UV value on the surface to change the height of each of the point. So you can see that the UV is running like a diagonally for the top of the faces and horizontally on the bottom and so on. So use those UV information to change the height of the surface. Yeah, that's like that. So to do that, let's create another pig head. Okay, for this one, I'm going to try to use the current UV set to this pig head. So the already set UV values, I would like to use the already set UV values for this pig head. So to see what it looks like, you can use this UV quick shade. How it looks like, so it looks like this. So pretty much the same as the previous one, like this one. A bit different, but pretty much the same. Okay, now there are a bit the point number for this geometry is a bit less, a bit not enough. So I'm going to create more points, preserving the geometry shape by using a subdivide node. Oops. Subdivide node. Okay, and check this with the UV. I'm going to subdivide like 3 times, so having tons of points like this, tons of smoothed out points. Okay, looks good. Now, and let's also check the vertex and check that you still have the UV value. Yeah, we do have. Now I am going to use a point wrangle to control each of the point. And first thing first, I'm going to retrieve the UV value for each of the point. So int vertex number point vertex at 0 ptnum and get the UV value using vertex function at vtx. Now we can see that the UV range is already in between 0 to 1, right? And I would like to use this UV value to convert it into an angle value to change the surface height based on this angle value, maybe using a trigonometry again to change. And specifically what I would like to do is to, looking back to the UV, let's say I'm looking at this section 5 here, and probably this direction is the U direction and this direction is the V direction. And I would like to create kind of a wave, a mountain-like wave for this U direction at specific distance and V direction at specific distance, and create a squared wave mountain at each of the divided square to create a pattern on top of a surface based on this UV value. So that's what I would like to try it out. Okay, so knowing that UV is in between 0 to 1, first thing I would like to do is to create a range, or divide this 0 to 1 range into some divided range, just like we did for the frames for the complex exercise for the Lerp. So to do that, I'm going to calculate the remains with a value less than 1. So if I do the calculation, if I do the modulus calculations for each of the UV value with, let's say, 0.5, then you get 2 ranges between 0 to 5 and 0 to 5. Okay, does it make sense? So what I mean is I'm going to calculate the modulus for UV using some 0.5 and 0.5. For the Z, that could be like anything, so I'm just gonna say it's 1. Since Z value is 0 for UV, so it doesn't matter what you use here. Now if you do this, then the UV range becomes split into two sections. So first of all, the U value is going to be split into two sections from 0 to 0.5 and 0 to 0.5. The 0.5 to 1.0 becomes 0 to 0.5. Same for the V, so you have 2 multiplied by 2, so you have 4 sections, 2 by 2 grid sections being created in this way. So make these values smaller for both U and V, you'll be able to get higher number of grid cells. So let's make this parameterized for X and Y. So let's start with 0.5 and 0.5. Okay, now what I want to do next is to remap this again so that each of the 0 to 0.5 range to become 0 to 1.0. For each of the grid range becomes 0 to 1.0 range as a target. So we could use like a fit function for that again. So UV fit, so UV is currently in between 0 to X, Y, Z, X, Y, 0, and then make this in between 0 to set 1, 1, 1, which is also equivalent to, if you don't want to use the fit function, then you could also use UV is equal to UV multiplied by set X, Y, or I mean 1 divided by X, 1 divided by Y, and or 0. This is also equivalent, but it's a bit hard to see what's going on with these calculations. This is shorter, but it's a bit more hard to understand by the first look, so maybe using this is more understandable for people who see your code. So I'm gonna use this with this. Okay, I got some errors. Okay, this has to be ch. I'm going to create an attribute, I mean the parameter, I mean the variable float x and float y, so that I can reuse this. Okay, so I'm going to replace this with x and y variable, and x is y. Okay, now it looks good. Now the UV value has several sections, and each of the sections the range is between 0 to 1. We can change this into an angle value, and since we want to have like a mountain like arc, we can use a range between 0 to pi and use that range together with the sign. Then you'll be able to have a value in between 0 to 1, which creates a mountain like wave. So you can just multiply this by pi so that the range will become 0 to pi. The 0 to 1 0 to 1 range becomes 0 to pi in this case. Or you can set pi right here as well if you want. Okay, now we can calculate the wave number for both U and V. So let's calculate separately. For the U height, I'm going to use sine UV dot x float YH sine UV dot Y. Okay, now that I have both height on U direction and V direction, I'm going to multiply those together and use it for the final height. So add P plus equal to the normal direction multiplied by XH multiplied by H. And seems like the amount of the height is a bit too big, so I'm going to reduce it by setting the maximum height as a parameter. Okay, so let's raise this up a little bit and see that you can see that the height of the face of this pig is being raised up. Now, since there's only two waves, two grid on UV direction, you cannot really see some grid-like pattern based on the UV. So let's make this smaller so that you have more grid faces. And let's also apply a normal on the last so that you have a better shaded view. Now you see that you have converted it to UV value into a grid-like surface. Use the UV value to create a grid-like surface pattern. Okay, let's go back and change those value. If I increase one of the grid value, you have more like a diagonal grid, which also looks interesting. You can also control how much it goes up, pop up, or if you make it negative, you can create this kind of inward pattern as well. Looks well. Let's limit the range of the height. In between, let's say negative 0.1 to 0.1 might be enough. Okay. Now let's create interesting shapes. And if you increase more numbers for the X and Y, you have less grid. So when it comes to 1, you don't see much changes. You see a bit of offset in the seams, but that's pretty much it. If you make it smaller, you see more grids happening. And keeping one of the values small and one of the value bigger creates kind of an interesting pattern like these. So that's one of the way you can use. A bit more complex way, you can use UV for some other purposes. In this case, I have used it to create a pattern based on the UV, a surface pattern based on the UV. And there are many possibilities using UV as well. And not only that, I mean, there are a bunch of ways, bunch of stuff you can use this UV. So maybe I could talk about this in other video as well. Now that's it for today's session. The topic was remapping. I have shown you the basics of remapping, how you can use like the fit function together with other several interesting functions for many purposes. If I come up with more ideas, maybe I could create another video on the same topic with a bit more complex examples. Anyway, when you do the procedural modeling, you do use this remap concept in most of the cases, and you cannot avoid using this. So knowing how the remapping could work, what's the technique out there for the remapping is, I think it's pretty essential. So please try to follow if you haven't used this kind of concept before. If you don't know what's happening there, if you didn't know what's happening there, then following this might help you doing a better remapping result or getting the better controlled result for the procedural modeling. Okay, so thank you for watching. And the next topic I would like to talk about is a VDV, control VDV with VEX, which is another type of volume. I have talk about how you can control the fog type volume together with the VEX, but next time I'm going to show you how you can control the VDV type, SDF type of volume, which is a bit more harder than the fog type. Okay, so that's it for today. Thank you for watching, and if you like the video, please like the video and subscribe the channel if you would like to see more of this kind of content. And I've also started the Patreon page myself, so if you like what I am doing, if you find these videos helpful or interesting, I would appreciate if you could support me to continue creating those videos. Okay, so thank you very much and see you next time.